Let me get something to drink, and if you guys don't mind, we can get started.
All right. Yeah, let's get the business meeting started then.
Yeah, go ahead.
All right. So I'd like to welcome everyone to the January 2021 meeting of the Mid-Atlantic Amateur Radio Club. Hope everyone had happy holidays and a happy new year. Now that 2020 is behind us, hopefully we'll have better days in the future. All right, so to get started, unfortunately, the virus still is out there, so all of our in-person events are canceled until further notice. So we will continue to have the virtual meetings at least through mid-year. Maybe optimistically, we'll be back in the second half of the year, but it may be longer than that. Fortunately, no breakfasts for now. The February VE session, which was supposed to be, I believe, in 2 weeks, that has been canceled as well. But what we do have going on are the nets on Wednesday and Sundays and these meetings right here. So to get started, I guess I should introduce myself. I'm Jeremy N2ZLQ. I am the club president. We did recently have some elections. Most of the board stayed the same. The big difference is that Rich and I switched places. So I want to thank Rich for his leadership over the last 2 years. I do have a plaque, which is on the way, but it hasn't arrived yet. So maybe at the next month's meeting, we'll do the formal presentation of that. So please join me in thanking Rich for his service.
Thank you.
And many more years, right? Mm-hmm. Okay, so let's go to introductions now. So we'll do this by the last letter of your call sign. So if the last letter of your call sign is Alpha through Echo, you can check in now.
Kilo 2 Hotel America. Fred in Broomall, Pennsylvania.
And K3NIE Bob here in Center City, Philadelphia.
Okay, how about Foxtrot through Kilo?
W3 JNF Jim in Springfield.
W3BOZ 3 Bravo Kilo Brian from Garnet Valley.
W3BOZ Tim or Boz from Westchester.
How about Lima through Papa?
Rich, KB3VZL.
Andrew.
Rich, K2RSJ.
Andrew, Kilo Alpha 2 Delta Delta Oscar.
Anybody else? Anybody else who wants to check in?
Bob N3JIZ.
I see Victor KB2UEH is checking in. See on YouTube, we have Bob W3REZ is checking in. Anyone else to check in this evening? All right, so to get started, our treasurer Lou can't be here this evening, but he sent me a report. He said, as of the last update, we have 47 members already signed up for 2021. That's a really good start. So please, if you haven't signed up yet, please do re-up as soon as possible. It does save Lou an extra trip to the mailbox to have to go out there. And our current current balance in the bank is $16,029.51. So Jim, any report from secretary or membership services?
Right now, nothing to report, nothing new.
Okay. But Bob, anything from public service?
No, nothing to report just yet. Hopefully we'll have something to report in the February meeting.
Okay. All right. As far as technical services, I don't see Dennis here, but I did have a little conversation with him recently. Apparently the 220 repeater in Bryn Mawr is down right now. We're trying to figure out what's going on with that. We do have some new repeaters and we're looking into options for getting those installed at the sites. Right now, probably not much is going to be happening with COVID, but we're having some discussions about what to do with that. So let's see what else is there. So a reminder, again, if you haven't renewed your dues already, please do so. You can find the address on the website. That's marc-radio.org. It's P.O. Box 557 in Eagleville, but I don't remember the zip code offhand. Just a check payable to MARC, M-A-R-C, for $20. Very reasonable, and that opens up all of the club services to you. All right, so a couple other ongoing events at the club. Our nets have been going on Wednesdays and Sundays on our 147.06 and 145.13 repeaters. We've been averaging about 15 check-ins, plus or minus a little bit each night, Wednesdays and Sundays at 8:30 p.m. They're going very well so far. We have a couple of good net control operators. I think Brian will be stepping in for the first time on Wednesday, so that'll be fun. Always great to get fresh meat operating on the nets. I think Mitch was supposed to do it, but he's under the weather right now, so he'll be taking Wednesday off. There is a new net. Philmont is running a net on their 147.03 repeater. They're advertising it as a drive time net, 5 p.m. Monday, Tuesday, Wednesday, Thursday, Friday. Actually checked in this evening. Seems like a pretty lively net. I think we had about 15 or so check-ins. So if you're looking for something to check into, give them a holler on 147.03. Of course, the Marple Newtown nets are 8:30 a.m. 7 days a week. That's on 147.195. They're always great to check in. One other thing that might be, actually, I have two other quick announcements. This upcoming weekend is the ARRL Winter Field Day. So if you want to find out more about that, just go to arrl.org or just Google Winter Field Day. I think that's usually a pretty fun event. I'm kind of busy with work right now, so I'm not going to be able to do much for that. And then also, the ARRL EPA section has a YouTube page now. So if you go to youtube.com, you type in ARRL EPA or EPA ARRL, and you'll find that. And they have a nice series called What Hams Do. And they've had a few of them now. They've had one on young people in amateur radio, and more recently one on mobile operating, and in particular, mobile emergency operating. And that brings me to one final point. You may remember from a year or two ago, there was a bill being considered in the Pennsylvania General Assembly, which would have essentially forbidden all two-way radio operation in cars. Thankfully, the Pennsylvania Senate seemed to have straightened that out by restoring the amateur radio exemption, but that bill apparently never made it into law, so they're trying again in this legislative session. I don't know much more about that right now, but I think the same person in the assembly who brought up the bill last time is bringing it up again, and I'm hoping that they will have the amateur radio exemption included. So other than that, I don't know too much about it. Is anyone else more current with what's going on with that bill?
No.
I watched the video, the ARRL EPA video, and it seemed to me that the reason they did that video was because the person who brought the exemption or brought the bill back to life again seems to have left out the amateur exemption. And so we're kind of back to square one with that. So I don't know what the ARL is going to do to proceed with getting that fixed, but it obviously needs to be fixed.
All right, so hopefully we'll be hearing more about that. Hopefully they'll straighten the bill out, and if not, maybe the Senate will catch it again. All right, so let's see. We're just about through announcements. Two more. Obviously, because of the virus, all of our summer events are in flux right now, so we're not sure what's going to happen with Field Day. It may look like Field Day last year, where we were kind of operating in our own homes. Maybe things will be better, that we'll be able to operate from Lower Providence. So right now, everything's kind of in a holding pattern. We hope to know more maybe in the next month or two. Maybe we'll have a better idea of how the vaccine rollout is going. As far as the Ham Fest, that's sort of in the same position right now. Right now, we don't know whether we'll be able to hold it. We are also looking for a Ham Fest chair or co-chair. I did handle the previous one back in 2019, but it's just beyond my capabilities right now to do that. So, I mean, I'm happy to help out as much as I can, but we will need someone who will be willing to be a chair or a co-chair. And again, that's if it's able to get off the ground, assuming that we've recovered to the point that we're able to. All right, so does anyone else have anything for the good of the organization?
I've got one comment. I'm on HF a lot. Boy, 10 meters is really wide open today, by the way, if you guys didn't notice that.
So hopefully solar activity's picking up.
Yeah, or something. Yeah, I've noticed that. Mid-morning, it opens up.
Maybe that bodes well for the winter field day.
Yeah.
Yeah, I hope so. I hope so.
All right, so let's move on to our program for the evening. Give you a little sneak preview of what's coming up. Next month in February, we'll have our very own John Huck, K3JH. He'll be talking about summits on the air. And in March, the meeting will be March 29th, which is actually the 5th Tuesday. We had to change it because we have a very special guest. We have Tim Duffy, K3LR, who's the CEO of DX Engineering. He gave us a really nice talk on antennas back in the fall. He'll be back in March, and he'll tell us the K3LR station story. He's got a really nice contest station out there. So if you think your station was good, wait till you see his. He's got multiple beams and all sorts of stuff, multiple operating positions. So he'll be there to tell us about that. All right, so this evening, we're also very privileged to have a guest joining us by the magic of Zoom. Joining us from all the way out in California is Ed Fong, WB6IQN. So Ed is kind of an antenna guru. He runs the website Ed's Antennas, which I sent you the link. He's designed a number of different antennas, and he teaches electrical engineering at UC Santa Cruz. So we're very happy to have him here this evening to talk to us about dual band J-pole antennas and any other projects that he's working on. Okay, so thank you, Ed. You can take it away.
Okay. Thank you very much, Jeremy. This looks like a pretty impressive group here. You guys look like you're sharp. Yeah. So get on field day this weekend. I'm going to be on. By the way, if we lose connection or lose power, then that's it. I don't know if you guys look at the news or not. We've got a storm that's brewing like you wouldn't believe. Oh, it's a big one. And I can start hearing it. Come on now. So that's why I want to get through this. They say by this evening, I mean, for here to get 3-4 inches of rain within an evening is a lot for us, by the way. I don't know how it is back there. That's a lot for us. I mean, I'm always okay because I'm not on a hill. But sometimes with the wind and everything, we'll lose internet. So if it goes, it goes. Anyway, let me share the screen here. First of all, I'm allowed to share. And here, this one. Okay. Okay, you see that?
Yeah, you can see it.
And then I go like this, right? Okay, that's how I'm used to sing. Alrighty, anyway, good evening here. Thanks a lot, Jeremy. Again, you guys look like a pretty polished group here, so I can probably zip through this a lot faster. You guys probably know a lot about antennas. And I'm not an antenna guru. I kind of play around with them. I teach them, and we do some simulations. And I've done some satellite antennas. We did the Cirrus Logic and the Cirrus antenna. That's the Cirrus Radio one, not Cirrus Logic. There are many antenna designers that are better than me. I just try to struggle along. I struggle along with circuits and communications and stuff like that. Anyway, my name's Ed Fong. I teach at UC Santa Cruz. This quarter, I'm teaching high-speed I/O optics. So, and then I usually teach an RF wireless class, and I teach what's called an introductory antenna class. So anyway, we're going to talk about how you dual band a J-pole today. And that's an interesting problem because it's a problem that a lot of people had about 20, 30 years ago. And I think the way I did it in QST is a pretty standard practice right now. In fact, a show of hands. How many of you folks have one of my antennas or our antennas? Oh, one. And Jeremy's got one, right? You have one, don't you? I don't hear your audio. It's okay. Anyway, you can buy them later if you want. We have plenty of sales. Right now, if you look at the website, in fact, we said we're down. We're not shipping right now. We're not going to ship for a few more weeks. COVID has just done tremendous for our business. And what I do is I have the students work on the antennas. It started out as, you know, how fundraisers, our ham club or our RF wireless group, they're not all hams at all RF wireless people. Years ago, I said, we got to raise some money. And we figured this is a great way. It's grown. Everyone thinks we're a company. No, we're not a company. It's me. At least 3 or 4 graduate students, three graduate students that help me right now. Then they vary, they come and go depending on the year. And we just try to make it. And then my daughter helps me out. My daughter's she's a graduate student in mechanical engineering. But she has a master's in what's called mechatronics. So she knows electronics well enough, but she's really a mechanical engineer. She always says, I'm not like my dad. No, I'm not going to be my dad. So I'm really a mechanical engineer. Anyway, so what we're going to start out with today is just introduce you to these articles that I did originally back in 2003. And then we have subsequent articles that we've done. It's in the ARRL Antenna Classics and the Compendium. So it's a pretty well-known design that's the ARRL has verified. They've got several models of our antennas there that they've tested. And usually when they publish it in QST or if it's in their ARRL handbooks or compendiums, they've tested it out there pretty as thoroughly as they can because they're very, very careful. They don't want to propagate bad information. So here we go. And so I guess you can interrupt. It's a pretty small group. If you really have a question or just wait for the end, make a little note. So I'm going to go through this pretty quick. The right side here is the original article. The left is the roll-up version we made of it. These are both in QST. One was 2003, 2007. Our most recent one is the tri-band version. Here's the tri-band version, which was in 2017. That was a request by FEMA primarily. FEMA says, can you make your antenna a tri-band because we want 220? And they do a lot of packet 220 because the packet doesn't interfere with 2 meters and UHF, because usually at an emergency operations center, you got all 3 bands going. And if you can keep packet on 220, you can continue the phone operations on UHF and VHF. But I find if you do packet on the same band, if you're trying to listen to like a handy talkie, way out there, it's tough because you just clobber it. The front end is just not linear enough for that. So that's why we made the tri-band. And that was quite a challenge. That's another talk we did. How did we make the tri-band? Who is it? Oh, my wife just came home from work. I thought dinner was here. So here's the patents. We had to patent some of this stuff. With the original DBJ2 that I'll talk about today, that was an original QST article. We did not patent. I just, we do stuff at work that we patent. I just didn't think it was patentable. Or I just didn't think it was that important. Only after that, I noticed that after we published it in QST, people started making them, they started selling them, and they're even selling them, calling them the Ed Fong antenna, and which is still okay with me. It was all right with me. I just thought that was, would I take someone's idea and build it and sell it for profit? I wouldn't, but I figured, well, I didn't patent it. It was in QST. But what upset at me was we started buying the ones that are out there, and none of them performed the way we wanted it to. And that was the problem. Kind of gives you a bad reputation if someone tries to build it or someone's selling it, because it is a tricky antenna. Now I'll go through it today. You got to have a really good network analyzer to build one. Of course, these days you just get one of these cool little things, right? A nano VNA and for $50, and it's a pretty good network analyzer. But back 20 years ago, you're left with pretty expensive ones like the MFJs and what other ones? MFJs, the Comets, and things like that. That's $400 or $500 range to go to UHF. But now it's $50, and they work really well. So we did have to patent it. So we ended up patenting our tri-band version, and we also ended up patenting how do you get gain out of a J-pole. And you hear all these interesting comments. We make a slim jim. I tried all that. That does not give you gain. It's quite elaborate. So that's another talk we give. So I give several talks. I give a talk on the tri-band, how to get gain. I give one on what do I call it? My love of the walkie-talkie. It's basically my personal story about, like a lot of you guys, I'm sure, when you're in the 1960s, you looked at the Night Kit and the Heath Kits and those little walkie-talkies, the cheap B ones that you would build. And I started like that, and eventually I got into ham radio. So, and I collect all the military walkie-talkies, some spy radios. I give a little talk on that of what I know about them. So that's another talk here. Okay, so let's start this about the antennas. I choose a J-pole. Actually, I'm sure a lot of you folks use J-poles. Now, I know when I was growing up in the 60s, we were using ground planes. Everyone just built a ground plane out of a hangar, out of an SO239 connector. And, not understanding a lot about antennas. The only meter we had that we can afford was an SWR meter, right? Like, I think most of us are like that. At 13, 14 years old, you're not going to buy an HP network analyzer. You buy this cheap Radio Shack, or you get at the ham club some SWR meter, and then you find it, they didn't have the internet. You look it up in a manual, and they say, hey, build a ground plane and measure the SWR. To us, that was pretty fun. Well, it turns out that a ground plane with radios, which again, I'm sure a lot of you have built, is not the most ideal antenna. Probably the worst case of it is that it's got radios. They tend to break because you torque it, right? If it's got radios, over time, it's got force coming down, and they will fall off and they will break unless they're built of really, really good steel. But whenever I would solder radios on, you guys know solder is pretty soft. You would solder radios on 2 meters. That's 18 inches. That's actually a lot of weight on it, and eventually the solder cracks because of the weight on it. So that is not good about the ground planes. The other thing is most ground planes are open circuit antennas. In other words, it's not a DC short. The radiating element and the radials, the same goes for a dipole, right? It's an open circuit. The good thing about a J-pole is it's a DC short circuit. DC short circuit, the advantage of that is that you don't need a lightning arrestor. It's always a DC short. I mean, it's 50 ohms at where you want it, of course, but a DC, so it doesn't build up charge, it just shorts out. And I'll get into this later. It also has a very good ideal dipole pattern vertically. Oh, and it's also end-fed. That's the other advantage. And we'll talk about that too. So here, I took this photo a few years ago up on Mount Sutro. Really cool photo with all the fog and everything in San Francisco. This is one of the main towers there. And you look at it today, I don't have a picture of it. Maybe I can find one of it 30, 40 years ago. You would have seen most antennas were ground planes by seeing the radials. I can't find a single antenna anymore that has radials. They're all verticals, all pure verticals, which means they're probably mostly of a J-pole type design. Again, the J-pole type design I'll get into is a DC short, does not need a lightning arrestor. When you use a ground plane or a dipole, you need a lightning arrestor. And for a good VHF, UHF, when you're talking a few $100s. And that's the good thing about engineering. Engineering, you can kind of design something out. Quite often it happens at a new design, you don't need this. Engineering is about saving money and getting the performance up. So in a J-pole, you don't need a lightning arrestor, and the performance is still very, very good. See, here's an example of a dipole, vertical dipole, hanging off a mast. Actually, it's a gutter there, but hanging off a mast. Good picture of one. A dipole, there's an insulator here. It's an open circuit, so it can pick up very high voltages. If there's a lightning a mile away, it will induce, if it induces as much as 30, 40 volts, goes down to your front end, it burns it up. So you need some type of lightning arrestor protection in this line that says that it exceeds 30, 40 volts, short circuits. So it protects you. Well, in a J-pole, you find you don't need this. And see, again, you look at this and you say, well, how bad is it? Over time, you'll know how bad it is. Open circuit, that's not good. But look how you have to feed it. Right angles. It works fine. This antenna works fine, but you have to feed it at right angles because if it was parallel, you'll screw up the matching. You have to feed it at right angles. There's some basic E&M theory not to interfere, which means you have to put an arm here. And a mechanical engineer will tell you, this one's okay because it's using copper pipe, which is kind of expensive. But if you want a really high performance, you should get this way out because this mass has still got to interfere. You see this copper pipe here? It may not affect the SWR that much, but certainly it affects the pattern, right? You can go on Easy Neck or ADS and, you put a parallel and conductor like that. It looks like you're maybe a foot or so on 2 meters. It's got to affect it. It affects the pattern tremendously. So that's not good. And plus, look at the torque. The further you go out, the force at that point, right? Most of you guys look like you're engineers. It's called R cross F. It's the torque. It's the distance times the force here. The force here is gravity. The further this arm goes out, the more force there is there. And what holds that together? solder. You solder the pipe. I mean, it'll hold together for years, but you'll find that in windy areas like up on hills, this is not a good design. They snap off after a while. So got a bad pattern. They snap off, kind of hard to mount. But if you can do this, do they work? Yeah, they work. They work fine. So I was introduced to this J-pole design by Denny Monticelli, and we'll show a picture of it in a while. And overall, it's a very, very good design. It's vertical, it's end fed, so you don't have to hang it off 90 degrees. When you compare it, its performance is about 1.6 dB better than a ground plane. And let me show you why. Can I? Yeah, here's the J-pole. And here's a radiating element here. That's halfway, 37, 38 inches for VHF. In a ground plane, you would have ground radials. And in ground radials, of course, it will only be about a quarter wave, 19 inches. So an advantage of a ground plane is it's not too tall. It's quarter wave with ground radials. The problem is this, in terms of performance, it's the ground radials that pull the wave down. And if they were at 90 degrees, that's why you kind of put them at 45. If they were at 90 degrees, it wouldn't pull the wave down far enough, as opposed to a halfway vertical dipole. This is a halfway vertical dipole. And imagine this is the center of the dipole. So ignore the bottom first. This is just a half wave dipole, twin lead. You feed it in the center. What's pulling the wave down? The other quarter wave piece down here. So it pulls it pretty hard. It pulls the wave pretty hard, as opposed to a ground plane. The radials are at 90 degrees. It doesn't pull it as hard. And you say, well, how do you quantify that? Well, if you actually model it, the difference is about 1.6 dB, about 1.5 to 1.6 dB at the horizon. In other words, the signal on a ground plane tends to go up to the sky, while on a vertical dipole, it pulls a little harder down. But we'll show you a pattern of it in a while. So let's go back here. So actually, it has excellent. It's pretty simple. It's end fed. And if it's end fed, you don't have to feed it at right angle, so you don't torque it, so it'll last for years. And this is 18,000. Actually, we've sold in our model about 30,000 today. We've sold quite a few of these. So I didn't invent the J-pole. That's already I was introduced to it. But what I've contributed to it is, how do you get it to work on UHF also and simultaneously on VHF? Because what happened in the mid 90s, we started getting a lot of these dual band handy talkies, dual band mobiles, and a lot of cheap hams. They didn't want to go buy a commercial VHF, UHF antenna. I don't blame them. It's $100, 75 to $100 for a good one. More these days. And a lot of us had J-poles or ground planes. And we have swap meets just like you guys. We're walking up and down swap meet in the mid-90s. Hey, we need a good antenna. And what's interesting was some guys will say, hey, my single band VHF antenna seems to work at UHF. Why would I need a new antenna? And then you talk to other people who says, yeah, it kind of resonates, but it doesn't work very well. And that's absolutely true. Most antennas, for you guys that are engineers, most antennas will resonate at their odd harmonics. In other words, if you make 100 megahertz dipole, just a simple 100 megahertz dipole, and if you put an SWR meter on it or network analyzer, you will see that it will resonate at 300, 500, 700, 900, 1100, and etc. It will resonate, but it won't perform very well. It'll be the patterns will be all over the place. So, and I'll give you an example here. This is how it would resonate. A vertical dipole, like what we showed previously, or the J-pole, this J-pole design is a vertical dipole. It's just the way you feed it. I'll show you how we feed it. It gives us, very well-known donut pattern. That's the figure 8 donut pattern. So the dipole is vertical, and you can imagine here's the sky, here's the earth. So, and then here you're sitting, you're transmitting here, and you're sitting here, and it gives you this pattern of a figure 8 pattern, which is not bad because it's better than the wave going up into the sky. That's the sky. It forms a nice donut figure, which means that the energy that you would think would go up in the sky is not going into the sky. It forms a null right at the vertical, and it kind of sprays out in both directions. So actually, that's a good antenna. It may not be a good antenna if you want to talk to someone here in the sky, like the International Space Station, but if you're talking to another repeater terrestrially, it's not a bad idea, a vertical dipole. Now, what happens though, if you put it at its third harmonic, you will still get a reasonable SWR. But if you go on EasyNet or ADS or one of these simulation programs, so this is the sky and this is the Earth, the pattern looks like this. Some people call it the four-leaf clover, right? You get four-leaf clovers. And really, the lobe that you want is over here. You're standing over here and, hey, 75% of my energy is going up into the sky or going down in the Earth. It's not going horizontally, or I might be standing right here. I want that distance to be the furthest, not up in the sky. So people notice this. They'll say, yeah, it has good SWR, but I'm losing quite a bit of signal. Well, it turns out when you quantify this, if you really look at this pattern, there's only 25% of it going into the horizon at the third harmonic. So what it says is, if you use a VHF antenna, vertical, and you use it at UHF, it will work. And the good news is it won't blow out your radio, but it won't perform very well unless you're talking to an airplane or to the International Space Station or one of the satellites. You can even use satellite work. This will work because the satellite's flying overhead and hey, you're just pointing up in the sky. It's great. But if you're trying to talk to someone terrestrially, no, it's not good at UHF. You only have about 25% of your power, which is about 6 dB. And that's what we measure. When you actually measure it, it's about 6 dB. So that's not what you want. We want to fix that. We want both at VHF and UHF to look like this nice pattern. So how do we do that without getting real complicated, right? Because here, if you find a solution, it's got to be, for hams, it's got to be pretty simplistic. You got to be able to duplicate it. You can't require some $50,000 network analyzer. And the other interesting things I think I mentioned it here. No inductors off the shelf or capacitors. When you're up at VHF, UHF, it's a bad idea to think, and especially an antenna, to think you can require a capacitor that you can buy off the shelf. Its tolerance wouldn't be good enough. Change with age. Inductors are very expensive. You buy it, if you wind your own, that's one thing. But if you have an actual inductor, rather than not have you get to go buy some inductor, more than likely it won't perform very well. And the likelihood that it will, if you publish in a magazine, go get this inductor, the likelihood that they have it in stock or whether it's within 10% or whatever is questionable. So you don't want that. You need a design that you can reproduce fairly easily. And we think that the one we have does that fairly well. Here's the pattern. So again, what's our goal here? Our goal is that the third harmonic not to look like this. The third harmonic, we want the fundamental to look like this and also the third harmonic. Then it'll work at VHF, UHF, giving us a dual band antenna. Yeah, in fact, this is our EasyNet simulation. So most of you guys should have EasyNet. So the only thing you have to understand in this is the Smith chart. I'm not going to teach Smith charts here, but you more advanced hams will know that a Smith chart represents a half wave all the way around or a quarter wave halfway around. So that the beauty of this is it says if you start out with a short circuit on a transmission line, a short circuit, and you go a distance of a quarter wave, and if you were to read the impedance there, it would be infinity. Hard to imagine. This is how I know, by the way, my graduate students, when I ask them this question when they first get introduced to it, they want to be, they want to be wireless engineers, not because they want to be hams, but because there's a job market in 5G and all this. And you test them. Are you really interested in radio? Because if you are, you will know that if it's zero, if I have a dead short, and in fact I do this, I give them a stuff. Hang on, let me get one here. Here you go. What I do is in one of my lectures, one of the earlier ones, I said, here's a piece of coax. I tell them, it's not a trick. It's just a piece of coax that I've cut. And I say, well, it's an open circuit here. I haven't shorted it. And you can get a DC multimeter. It's an open circuit. So what is it on this side? You get a DC meter because it's open circuit. And I says, well, what happens if this is about 5.5 inches? What happens if I short it here? If I short it here, well, what is it here? They would say, well, short circuit. And it says, well, what if it's a short here? What is it here at 450 megahertz? Then I would say the people that are non-hams or not RF engineers, not experienced RF engineers would say, well, if you short it on one end, it should be a short on the other end. And of course, you RF guys know that's not true. If it's a quarter wave, a short will be an open, and an open will be a short. Exactly the opposite of what you would think. And you would say, is that bad or good? Well, it's just a phenomenon that you can use to your advantage. And it's used all the time in antenna design, understanding that. So this is how we explain a J-pole. The J coming from just the way it looks here, you look at follow here, and it looks like a J. So what we start out with is so this is twin lead, so you need this other piece or just floating. You don't need this. This is the original design I saw. It used a 300 ohm twin lead. So that you can throw this out. It's not part of the antenna. But here's the half wave right here, 37, 38 inches, depending what frequency you're at. And it's center fed, right? So typically you would have a arm here to feed it as a dipole, and then you have a mass like what I showed you before. And does that work? Yeah, it works. But again, you need to put an arm here, and you need to hold it up, and then that reflecting mass should not be metallic. If it is, it'll affect the pattern. You know, at a few feet, it probably won't affect the SWR, but it'll certainly affect the pattern. Even at 3, 4, 5, 6 feet away, it'll affect the pattern. So the goal here is not to feed it in the middle there because of all those problems. It'll blow down the wind because of the torque and the reflection of the mass. So here's a clever way that I guess the patents are but 50, 60 years old here on these. You feed it here. It's going to be a high impedance. It's low impedance in the middle, 60, 70 ohms. At the end, that's where it's high in voltage, low in current, which means it's high impedance. At the end of a dipole, it's high impedance. We would like to feed it there because if we can feed it like this, we can make a full vertical, and we can. It's a high impedance there. So you need to transform your 50 ohms cable or your generator, your radio, 50 ohms into something that's high impedance. What we call high in RF, in the thousands, clearly in the multiple thousands of ohms. Because that's the impedance at the end of a dipole. So how do you do that? Again, we go back to that Smith chart. It says, if you short the bottom, a quarter wave later, it will be an open or a high impedance. So although it's a DC short here, it's a DC short there, but it's not a short at its resonant frequency. It's at its quarter wave point. It is not a short. It's an open. Probably not infinity in RF, in several thousands of ohms for sure. So if this transforms a short circuit here, and you go a quarter wave, it's an open circuit according to the Smith chart, at least a very high impedance, then we can match it because the end of a dipole is also high impedance. Now, the question you ask is this, quite often, hey, you've only got 15 1/4 and 1 1/4. Isn't that 16 1/2? And shouldn't it be more like 18? It would be if it were in air, but since it's in the twin lead, it's in plastic, you will slow down the speed of light. That's called the velocity factor. Light or air, free space being 1, the velocity factor, and then it goes down from there. You know, for example, water is half approximately, which says if you were to take an antenna in air resonating like 2 meters or 18 inches on each side, if you were to dip that all the way in water, it would be about half the size for resonance, about half in distilled water. So when you're in the twin lead wire, it's got plastic that holds it together. So it slows down the speed of light. It's an air that it's 1. So it's more like 0.8 or so. It slows it down by maybe 20%. So in the end, instead of about 18, 19 inches, it's only 16 and a quarter to make it match. And then since the short down here, the short's still 0 ohms. And if it's an open up here, it just, with reasoning, you say, well, there must be 50 ohms someplace. And it is, there is. About 1.25 inches up. You can find it with a network analyzer, right? If it's 0 here and it's close to infinity here, or at least ideally infinity, it's got to be 50 ohms. And logic will show you 50 ohms is closer to 0 than it is to infinity. So it's probably, instead of being up here, it's down here. And sure enough, it works that way. So here are examples. Here are examples of J-poles. Again, here's a home built one with copper pipe. That's the vertical element right here. That's the 37, 38 inch piece. Here is the quarter wave stub. So here's a short circuit. So as you move up this, you're making this transmission line out of air, out of 2 pieces of copper pipe. As you move up here, the impedance of this transmission line is going to get higher and higher and higher to a point where you hope that as it gets to the end of the half wave dipole, that it's a fairly high impedance. That's on the other side of the Smith chart. And then you can just tap it off here at the bottom. Since this is 0 ohms, you can tap it off. This is about 1.5 inches in this case. It's going to be 50 ohms. And does this work? Yeah, it works because we've built them. In fact, I have one right here. We build these in our class just to show how antennas work. They have different varieties. And here's the short, and here's the jump. Just like what you see in the picture. What's wrong with this? It works fine. It works fine on VHF. Oh, somebody's mic is on. Mute. Okay, is it muted? Okay, so it works fine. Again, a short circuit, so about 1.5 to 2 inches up. We tap it, and that's 50 ohms. The only problem is when you make it out of copper pipe. Oh, I hear my dinner. Dinner's here?
It's on its way.
It's on its way? What's this? Oh, okay. Oh, good.
Maybe at max 10.
Well, fine. I'll be over then. Anyway, when you build this, so be careful if you have one of these, that it'll work at VHF pretty well, actually. It works pretty well because it's a transmission line, right? This is a transmission line, and this is the 50 ohm point. The thing is, at VHF, quarter wave is about 18 inches, and this is about 1.5 inches. This is still a reasonable transmission line, not optimum, but that's reasonable. That's why the thing works. At UHF, the problem with UHF, this is already about 2 inches. UHF, the quarter wave is about 5 to 6 inches, depending on what frequency you're in. 5 to 6 inches. Well, you have an UHF antenna already radiating there. In fact, it's even radiating in the wrong direction. It's horizontally polarized. So that's why this is okay for VHF, but not for UHF. For UHF, that does not make a good enough transmission line here. And plus, you lose quite a bit here with almost a 2-inch jump. That's just too much exposed, so it starts radiating in the wrong direction. You lose too much energy. And on top of that, of course, once you get the energy in, this is, again, going to a third harmonic radiator, which means it'll have that weird pattern that we showed you. And our whole idea is to get rid of it. But that's the basic J-pole. And would it work? Again, this one doesn't work that well because of this problem. It's just too far split. But here, let me show you another solution. Here's another solution to try to get that third band, or not the third harmonic, second band out of it. So what it says is, if I feed a UHF signal into a 2-meter type antenna, I'm going to lose about 75% of my equivalent radiating power. You need to put a UHF antenna in there also. I mean, it'll resonate, but it doesn't work very well. So Arrow came up with this design a few years back, and that's a clever design. They took a J-pole and put kind of 2 in parallel. They took the transmission line of the VHF, but made it the radiating element for the UHF, and then added another piece, or it's actually about 6 to 6.5 inches, depending on the frequency you want. And the lower UHF band will be 6.5, but if you reach the phone band, that's about 6 inches. in air. So it's about 6 inches. So what happens on this antenna is the UHF portion becomes here, and the VHF antenna is this part here. And they use the same feed point. You have to see how the feed point, it's nothing fancy. It works out that you can use the same feed point there. Does this antenna work? Yeah, it seems to work pretty well in VHF, even reasonably well at UHF. There's only one flaw here that I can see is, so here's the UHF antenna and here's the VHF antenna. The problem you have, so the VHF antenna, if it's resonant, will grab, let's say you have a UHF signal, half of the signal will go into the VHF antenna and half of it will go into the UHF antenna. You want all of it to go over the UHF antenna. Unfortunately, this doesn't do that. Half and half. You know, if the match, let's just for simplicity, assume that the matching's good both at VHF and UHF in an equal level. So just half and half. The problem is the half of the energy, half of your power is going into this VHF antenna at UHF. Half of it will have the weird pattern. The good news is the other half will not. Now, it will still have some reflections because that's a conductor vertically with your UHF antenna. So it will be biased, obviously, and reflect a little bit. But this will resonate and it will work reasonably well, losing maybe 25% of your energy compared to, you know, a full J-pole at UHF. The other configuration you see quite often is a Slim Jim. The Slim Jim, when we analyze this, all it is it's just a vertical J-pole, single band, nothing fancy. Somehow someone got this idea when you short the top of the twin lead, you get 6 dB. It doesn't make a whole lot of sense to me. We've simulated it. The good news is if you buy what people call a Slim Jim, it works fine. Works fine on 2 meters. Suffers the same problem at UHF. Still losing about 6 dB or so. But, you know, for 2 meters, it's fine. I have no problem with it. But it does not give you the 6 dB gain that some of these people say. Just by, you know, instead of letting this piece float, you tie it together. They're too close together. It just looks like one piece of wire. Okay, so how do we dual band this? Now that we've talked about single banding it. Pretty straightforward, actually. You take the 2 meter version of the J-pole. And remember, I always said, here's the bottom. We haven't changed the bottom at all. Still 16¼ inch. 15 plus 1, 15¼ plus 1¼ so 16, I'm sorry, 16½ inch, 16½ inch. Well, remember we said the matching was never the problem. This obviously, this is used too well for VHF. That's a quarter wave matching stub. But at UHF, it's a 3/4 wave matching stub. So it'll wind back up, still high impedance. 3/4 meaning if you go up a quarter at UHF and then you put up another half wave like that, you're still at a high impedance node. So that's why when you always add another half wavelength at any point you're at, you're back at the same impedance because you're going, the Smith chart represents 1 half wave. So if you go 1 half wave around, you're back at the same point. So what does that say? That says the matching up to this point is both good at VHF and UHF. No problem with that. The problem is with a UHF signal launching, once you launch it off, you know, from 50 ohms, high impedance wave kit, so you launch it off. It doesn't know what's here yet, but you launch it off. What it would like to see is a half wave, like 11 or 12 inches. And if it saw that, it would be great. It would be a half wave vertical, assuming all this is, the top here is not there. But it is there. That's the thing. In a regular J-pole, you go up 12 inches or so, but the rest of it's still there. So that's the problem. If you feed a UHF signal here, oh, it couples at this point, high impedance to high impedance, it's fine. Problem is, it would like to see about 11 to 12 inches. It doesn't. It sees 37 inches. It goes up 12 inches and it's still continuing. So the currents, the induced currents will continue to go. Well, if it continues to go, the problem is the pattern will go up, right? If the current is going up, the wave is just going to be bent higher and higher. The wave gets bent up, and that's where you get, that's where basically you can explain those lobes. You haven't stopped the current. But you can stop the current by adding a little stub, right? If you add this little stub, the short, It's 4¼ 4.5 inches. That is a quarter wave at UHF for RG174. Again, it's not 5 or 6 inches because that's an air. This is in the dielectric material, which is, that varies 0.7, 0.8 in that range. So it isn't 5 inches if you ever to make a quarter wave stub at UHF with coax. It's about 4 and 4¼ to 4.5, 4 3/4 in that range, because it's not going to be 5 or 6 inches because of the material itself. That's an air. But the goal of it is that if I short one end, it would be an open or a fairly high impedance in the other. If you can do that, what happens at UHF is when you shove a UHF signal, it comes here and electrically it's as if this wasn't there. It's high impedance. It's as if it's not there. So therefore the currents can't continue. You don't get the lobes. And here is the roll-up version of it. One of my students came up with this years ago. He said, hey, you can make a roll-up of this. And it's where he goes to this more mechanically, how you make the cuts could all hold together. And yeah, we managed to get it all hold together with heat shrinkable tubing and all that. The first thing you'll notice about the roll-up version or the portable version of it, it's a little longer. It's actually about 2 inches, 1 to 2 inches, about more like 2 inches longer. Why is it longer? Because the base station version goes into a PVC pipe. And the good thing is the feed point is at the bottom or it's at the end. So you just feed it from the bottom. You feed it in the pipe. Why do you put it in the pipe? So it can last. UV plastic is UV protected. It's more rugged. So I'll show you one, of course. Let's see. PVC pipe. You put the antenna in PVC pipe, and this stuff is great. I mean, I didn't invent it, but DuPont or whoever it is invents, they've got it UV treated, and this stuff lasts for years. It's the same formula that they put in the 30-year vinyl windows. 30-year vinyl windows are fine. I've had one of these now going on 18 years at a repeater site. Make sure you cup it tight, and it'll hold up in the sun. It'll hold up in Arizona desert. It's designed that way, and it's cheap. But it does shorten the antenna a little bit because, again, when you cover the antenna, you'll slow down the speed of light by maybe 3 or 4%. So the antenna is a little shorter. So for example, if you were to if you were to take this design here, which is designed to go in the pipe, and you just hang it in air, the resonant frequency will go up about 2 or 3 megahertz because it's designed for pipe. So this one is a little bit longer. It's about actually about 1.5 to 2 inches longer because it operates in air. Okay. Yeah, so so dimensions are a little bit different. It's because of the velocity factor. And the pipe we recommend, the coverage, you figure, this says, Ed ever studied pipes? Yeah, actually, I had a master's student study different pipes on antennas. And you figure, wow, how hard can that be? Well, to analyze it, it's a lot of work. But the basic conclusion is buy Lowell's 23990. It's cheap, it's thin, it works fine. The attenuation factor or the loss tangent is very low. And the way you can figure this out is it's very simple. His thesis may have been thick, but the conclusions are pretty straightforward. You want to test out a material that you want to cover an antenna with. It's got a fairly low loss tangent, very simple. Made a tremendous correlation. Take the material, put it in your microwave oven for 5 minutes. If it heats up, it's no good. But if it stays cool, that means it's good. That means it doesn't absorb RF. And we had very good correlation on that. We found that the Lowell stuff pretty cheap. If you can find it for 5 feet, they're about $1.50. Most of them just sell them in 10 feet sections. That's like $2.50. But $2.50 is nothing. You get 2 antennas out of it. And again, it should last for 30 years. I've got one up 18 years up, and that's on a repeater site. Storms, hot sun. Like today, it's going to take a beating. I have no fear that it's going to come down or anything. It's been up there 18 years, and it works fine. So the question is, this little stub idea, you put this little stub to suppress the antenna for the rest of the antenna. Does it work? Well, here is proof in the pudding. Here we have a 2-meter J-pole at UHF as a reference. Remember, it's not supposed to work at UHF. You use our design, same condition, as same as it can get, This is an HP 8591 spectrum analyzer. And it was just tested on a Sunday out in an open parking lot. You put our antenna and with that stub at UHF, it gains about 6 dB, clearly 6 dB. It really does work. That's 10 dB per division. And if you look at the numbers, go through this real quick. These were taken 5 measurements under 3 days. When you test antennas, that's the other thing. The person that did this, he didn't realize that it takes quite a bit of work. You got to make sure you have 3 separate days: foggy, sunny, rainy. Those are the 3 days. And each day, take 5 measurements and take the average, and make sure they don't deviate by a lot, because if they deviate, you have a measurement error. Make sure they're fairly consistent, and then you take the average. Here's the averages. So this is how it works out. Here's a quarter wave mobile. That's just the reference, minus 24.7 dB. That's a reference. It's ground plane, basically. You get a rubber duck, yeah, you lose about 6 dB. That's what they say, about 6 dB. That's why you try not to use a rubber duck when you don't have to, unless the signal's pretty strong. A standard JPO, yeah, it is better. That's not by much, minus 24.7, minus 23.34. It is about clearly over a dB better. Is that significant? Not significant, but in a weak signal, probably noticeable. You could probably hear the difference in a weak signal. Our antenna, about the same as the standard JPO, pretty damn close. We probably lose like 0.1 dB, it looks like, and it's pretty rest assuring that was not error, because that's a 15. There's 15 measurements done here, taking the average. Yeah, you probably do lose about 0.1 dB. Probably due to the losses of that stub, the wave probably loses a little bit. Not much. I mean, I would say it'd be very, very difficult to actually detect on an actual conversation. You could probably measure it with critical equipment. Now, how well does the antenna now perform at UHF versus a UHF antenna? There's a quarter wave mobile antenna at UHF. At UHF, you compare it to a rubber duck. Well, a rubber duck at UHF is actually pretty good. We've actually found some that are very, very good, almost comparable to a quarter wave. Because, again, UHF quarter wave is about 5 or 6 inches, a rubber duck 5 or 6 inches. So you can actually get a UHF rubber duck and a handy talkie to work quite well. It just requires some good matching. And a standard VHF JPO at UHF, it's terrible. It's minus 45 dB. It's worse than a ground plane. A ground plane quarter wave is minus 38. This is just a reference, 38. You put down that a standard VHF JPO at the same frequency at UHF, not UHF, man, minus 45. That's 5, 6, 7, not quite 7 dB, 7 dB of loss. That's something you can't afford. 7 dB is a lot, right? Remember, every 3 dB is half the power. You're losing 75% of the power when you use a VHF antenna at UHF. So in an emergency, sure, it will work, but it's not a very good performing antenna. Now, our antenna with that little stub, so you stop the wave from continuing, not bad. Minus 38.9. Again, it's within 0.1 dB. So I'm not saying it's lossless, but it's really, really good. Engineer, good enough. Mathematician, they'll say, try to gain back that 0.1 dB. It's hard to find because we have that stub in there. And so, yeah, it does lose a little bit, but it's not much. It's insignificant. So here's our lab here. That's that's an old picture of me with our old network analyzer, old reliable. But, these days, $50. That's a good analyzer. Show of hands. Who's got one of these? Jeremy, you don't got one of these? You guys got to buy one. Up to 1.5 gig, you can tune duplexers, filters, antennas. Go to R&L Electronics. Oh man, I smell food in the other room. It's dinner time. See, we're 3-hour difference there. It's 6:15, dinner time. So that's our HP. We still have that, by the way. It's a very good, reliable unit. But that was $80,000 20 years ago, about 18 years ago. Okay, so the other thing people look at is that little stub. That's the little shaky part. That's the part you added. How is that stub? It's actually pretty good. I measured the impedance at 445 megahertz. Again, it's actually right there. Is it infinity? Nothing's infinity, just like nothing's short. It's high. Let's say it's a high impedance. It could be higher, but it's higher than 50 ohms. I tell you that much. It's a several thousand ohms right there. And here's, sweep another frequency. We're sweeping it from 30 megahertz to 1 gig. So at 445, it almost falls right at infinity. Not quite, but close enough. And then I put my hand around it, pretty stable. 445, it's still pretty good. And then I look at a wire. Here it is at 146 megahertz. It's right about there, 146. I look at a piece of wire. Hey, a piece of wire is actually right there too. At 146, they're close enough, but probably not the same. That's why we're losing that 0.1 dB. So see here, the NFET, good picture of an NFET. The whole antenna's in there. It's right at the bottom. It's NFET. It makes it a lot easier. The weight is all vertical. You don't have torquing. It is taller. It is 3/4 of a wave as opposed to a quarter wave. But if you really trade it off and talk to folks, we'd rather have a 3/4 wave tall than have things hang out of it, or in a dipole, have an arm. That would just break off. And it performs like a half-wave dipole. And it's good. It's covered in cheap $2 PVC pipe. You can't beat it. And here's our roll-up version. The roll-up version, we sell, that's the actual antenna. We sell it with a 6 feet extension, and we sell it with all the adapters. One of my students suggests that because, what most people use this on a handy talkie or portable. They'll use SMA or SMA reverse or BNC or something. Why don't we just include all that and just buy it by we buy it in the thousands and get the price break? Yeah, so that's what we did. And plus we include the 6 feet extension cable. See, and then a BNC male. So the extension cable is a BNC female to male. So you can just add them. And if you want to buy more, you can. So that's the end of this talk. But we have other talks. So here's how you get gain. We've got the tri-band version. I've got a DMR talk, and then I've got the walkie-talkie talk. So that's the end. Here's a good picture of tri-band radios. We give these as prizes usually at our club. I find that, hey, they're actually pretty good. I've used these. They're cheap. 2 meter, 220, 440, $99, 25-watt mobile. I find that the BTEC handy talkie tri-band, the UV5 is dual band, but the UV5 times 3 is tri-band. You can find this for about $30 to $40 on eBay on sale. They have a flash sale, so pretty reasonable. We did a cool project on a GP5. That's a software-defined handheld radio. You guys can look this up at the CountyCom website. Oh, by the way, Jeremy, I'll send you these slides. That radio we worked on in 2012. All on a chip, uses a Silicon Labs radio DSP chip, 22 bits. It covers, this is an HF, actually 100 kilohertz to 30 megahertz, all mode, receiver only. Operates on 3 penlight batteries. Very high precision readout. Anyway, if you guys need one, look it up. If you guys want one, they're $65. I think CountyCom sells them for like about $100. I don't know what they sell it to the government for. It was a government contract. But we could get a bunch of them if you guys are interested. And then we can sell these antennas. There's no rush. If you guys have them, there's no obligation or anything. We got plenty of business. So if you want the dual band one, we sell that in commercial or ham. It's $32. We get the roll up again, commercial or ham, $32. The tri-band goes for $65. Then extra cables, and we sell that, and then the radio goes for $65. But there's no obligation, believe me. We got plenty of business. If you want one, fine, but don't feel obligated just because I talk. You got to buy an antenna. Anyway, end of talk and open to questions. Go ahead.
All right, thanks so much, Ed. That was great.
Let me
Any questions?
do that. Yeah. Sure, ask questions. Hey, no, do any of you guys have the GP5 radio?
No.
But a few of you guys have the antenna. Yeah, you go look it up on CountyCom, their website. They have a little demo on it. That's a really cool radio, 22-bit DSP. I wrote the software for the single sideband detection on it. Basically, just cosine sine stuff. I was impressed with it. It lasts about 200 hours on a battery. Digital readout's got a good clock. It's even got a temperature control on a temperature, reads the temperature. The military had all these requirements, and CountyCom sells them for $100. Even for $100, it's quite a radio. In fact, the interesting story about it is Ron Kwan and Tom Lee over at Stanford, they worked on it too. And he says, hey, what we got to make is we got to make the companion transmitter, single sideband transmitter. So they've got the single sideband transmitter, same size, 1 watt, operates on 3 extra penlight batteries. That's one of the projects in their EE 406 class, a lab class. They make the single sideband transmitter for that receiver. And yeah, I cover that in my tri-band talk a little bit, the performance of it. It's a cool design on their transmitter. No inductors, all IQ modulation. They still get about 30 dB of sideband rejection and carrier rejection. But if you, that class, they have a little board, the kids build it and they characterize it. It's pretty cool. No questions? Come on, guys.
We have a question.
Sure.
So in the usual roll-up J-pole, a sort of traditional one with the twin lead, so that second wire that's disconnected, that really has no effect at all? There's no parasitic?
It's too close. Yeah, it's too close. Yeah.
So as long as it's much less than half wavelength or quarter wavelength.
Yeah, it's too close. Right. Exactly.
Now, I actually have the...
I bought one of your antennas. Yeah, hi there. Mark here, WA3QVU. I'm a friend of Lou's, WX3I. I bought one of your antennas a couple years ago for the GMRS band. The MS150, we do that over in Cherry Hill, set that up. Works perfect.
Oh, did you buy the dual band one? You have the dual band one or the dedicated GMRS one?
Dedicated GMRS.
Oh, that's a good one. Yeah.
Yeah, works perfect. Very well.
Yeah,
of course, I put it up about 30 feet in the air. That always helps.
Yeah, we're really busy. It's amazing how much of we've built a company, not intentionally, but just as a fundraising project. And over the years, I guess people spread the word. We've got orders way above our head now. My wife says, why don't you start a company? I go, that's not what I want to do for a living. It's just to start as a fundraiser. But boy, it's gone through the ham community. Then it gets into the commercial community. And by the way, that UHF one, that one came about from ATD alarms. They have a mesh network now because, in the old ATD alarms, you would have a phone line to the central station. Well, it's interesting what ATD does. We can't use a phone line. People watch the James Bond movies too often. The first thing a thief does is cut your phone lines. So they 20 years ago, maybe 15 years ago, invested in designing a whole mesh network of 2-watt radios. The FCC gave them a special license and they're networked. And then this way they don't, the other thing they said was when you had ATD alarms and it's not very expensive, $12 a month, $13 a month. Half of it was going to the phone company. Remember, ATD didn't own the phone company line. So they figured, wait a moment, we're giving half the money of this gross to the phone company? We got to find a better solution. So they have a whole mesh network now. Really cool because I helped them work on it, and they buy a lot of antennas from us, infinite amount of antennas. They're so they're like 2-watt transmitters. And if you're a neighbor close enough, they don't need an outdoor antenna. But if you're like in a remote area, 3 or 4 miles away from any other node, then they put one of our antennas outside. So we sell them quite a bit.
Cool.
That's how the UHF antenna came about, because they came to the university and says, you're an antenna guy. We're getting ripped off by Comet and Diamond, by the way, $100, $120 for VHF or UHF gain antenna. We'll give you big orders if you can make 5-6 dB gain for $30, $40. And actually they gave us a grant on it initially. And if you can make it, well, we're more than willing to pay you $30, $40. Well, we made it for them. Here it is. You check it out. 5 dB gain, no radials, rugged PVC pipe. What do you think? So they ordered tons from us, more than we can deliver. That's why I keep on telling you, you're not obligated to buy any of these antennas. If you want, great. We have plenty of business. Just enjoy the talks. And I'm glad to give you another talk. And there's no obligation.
So Ned had a question. So do you have any mobile options?
No mobile options. No, buy a Comet or a Diamond.
Question.
Yeah.
How does the mounting affect the SWR of the antennas?
Oh, the way we have the antennas, the lead-in wires are good 8 to 12 inches from the bottom. So as long as you keep it in the bottom, we find that the mounting's pretty independent. Oh, the other related question is balance and ferrite beads. A lot of people ask, do I have to wrap a coil around it, or do I need ferrite beads? So we did a bunch of experiments on ferrite beads. Yes, you do. When do you think you need ferrite beads, where it really helps? When your antenna is not resonating. This is my theory. If you need ferrite beads to suppress, I'm not saying they hurt. They never hurt you. The question is, how much do they help you? They help you a lot when your antenna is off resonant because of the common mode currents returning. The beads absorb it. And it's just like high power. You don't want all that reflected power going back into your radio. You'll blow up your radio. You want to convert into heat. That's exactly what they do. So they get their job done. But what we found is if the antenna is working right and all the energy, SWR is really low and 99 or 98% or 97% of your energy is going into the antenna, just the math says you don't have to suppress very much. Your antenna is working right. So what we find is if you stay within the ham band of our antennas, you're fine. If you start going out, sure. And I tell you, I've played around with ferrite beads. If you have a non-resonant antenna, you guys probably have too. And you say ferrite beads help? They do. Man, are they hot. You guys ever notice that? You touch a ferrite bead when an antenna is not resonant, it is too hot to touch. We're talking about 50, 60 watts. Way too hot to touch. So basically, when your ferrite beads are getting hot, my suggestion is I think you better find a better antenna or another antenna. Ferrite beads is just protecting your radio so it doesn't blow up. It's quite a heater, right? I mean, that's not a very efficient way of generating heat by ferrite beads. That's a terrible way. So that's my philosophy on ferrite beads. You need a better antenna.
Ed, do you think the ferrite beads help you where you're mounting the antenna on a steel mast or next to a steel mast?
Yeah, that's because you're mismatching it. You're right. If you're mismatching it, you better put some ferrite beads because when it's mismatched, where's the power go? It gets reflected back, and hopefully, if it's not a lot, you're okay. But if it's a lot, it can burn out your radio. So then the ferrite beads, it will convert it to heat.
How far out do you think we should mount the thing if we're putting it on a steel mast, next to a steel mast, like a tower? How far out do you have to go?
If the bottom 4 or 5 inches is fine. If you put it steel, it doesn't affect it.
Okay.
See, the good news also is, you notice it's a low impedance. If you look at the J pole, what's the bottom? It's a short. It's a low impedance. If it were a high impedance, it would be a lot more sensitive, but it's a low impedance. So you should actually have more than that even. So that's what I suggest. You're fine.
What if you're not at the top of the mast?
What's this?
What if you're
not at top of the mast?
Like on a tower leg, how far away do you have to put it?
Then you have to put, then you're in the same situation as a dipole. You got the arm coming out. Yeah, everyone has that problem. Then the further you get it out, the better off you are because then your mast doesn't act as the reflector. Then again, the further you go out, the more torque there is, right? Way out, you got R cross F now. And then if you're in a windy area, that's tough to handle. Okay. Yeah, I'm getting hungry. I'm sorry to say. It's dinner time.
All right. Thanks so much, Ed. That was a great presentation.
So you're very welcome. And then again, I'll email Jeremy the slides. You can forward it. And then I'll give you a list of the other talks I give. And if you got, the thing is, I can't say if you get desperate anymore, call me. Because now I have to limit my talks to 2 a month. Otherwise, my schoolwork just gets all tied up. And, believe me, I'm booked till November of this year. It's that bad. I mean, especially with COVID-19, everyone's doing Zoom. So call Ed Fong. Yeah, so I'm pretty booked. Unfortunately, I'm pretty booked. So I would normally say, hey, give me a call if you're stuck up for a speaker, but not anymore. The man, I mean, I'm sure all of you guys can come up with something you can talk about ham radio, and clubs would be more than glad to have you on Zoom. I ought to know. I'm one of the speaking chairmen in my two of my clubs of fine speakers. People are sick and tired of hearing from me for the last 10 years. After a while, now what's Ed up to? Oh, no. See, I know how it is. I know how it is. So anyway, hey, Jeremy, thanks a lot. I'll give you the slides. Right. And if you guys want to order, that's fine. No obligation. Absolutely no obligation.
All right. Thanks so much.
Thank you.
You betcha. I'm going to leave and go get my dinner.
All right.
See you guys later. Hey, thanks for having me.
All right.
Thank you.
Happy munching.
Thank you.
All right. Let me shut down the